Okay. So here I have just a collection. Let's assume they're just gas particles or dust particles. They all are gravitationally bound. So there's a bunch of particles here. They're going to undergo a huge number of collisions. They're all going to be moving to start with. And over time, they're all going to collapse down into a single object, essentially. But the thing is that if this is a closed system, then the total angular momentum in this system shouldn't change. And so if I pick some random point, probably at the center of mass, that'd be the most logical point. You find the center of mass, and then find each individual particle's angular momentum, MVR, and add them all together, then you should still have that same value. Once these all clump down into a single object, it should be rotating with that same angular momentum that you would get initially. And so angular momentum would therefore be conserved, right? Does that make sense? It's just in the absence of external. And now it's not, remember, in the absence of external forces, linear momentum is conserved. So in the absence of external, for angular momentum, spinny torques. In the absence of external torques, then angular momentum should be conserved. So there's internal torques, obviously, here, but there's no external torques. If there's external torques, then you get changes in angular momentum, right? And so now we have a single object, once this guy finally falls in, that's got a single angular velocity. And so if this was a perfect sphere, then it would be I omega, 2/5 mr squared, times the angular velocity in radians per second. And that value will not have changed. And the reason I bring that up is because when we have galaxies form, and really like protoplanetary disks, how solar systems form, whenever you have those form, you essentially have a three-dimensional cloud. This is what I was getting to last Friday before we ran out of time. But you essentially have a giant gas cloud that's 3 dimensions. So I'll try to three-dimensional gas cloud. But that gas cloud has a single angular momentum vector, and let's just say it happens to be here. That's the direction of its angular momentum. Meaning that everything's going to be swirling around it this way, right? But initially it's not. Initially we have collisions in all dimensions. But the collisions in this dimension are going to end up sapping the linear momentum in this direction, but it's going to be conserved in this direction. They're still going to all be moving. And the reason that the angular momentum vector points this way is because the net linear momentum in that direction is going to be very small, or 0. And so collisions between particles as they crash, they're going to sap the momentum, or the speeds, I should say, of the particles moving along the angular momentum vector, but they're still going to be spinning around, as we just showed in that simulation. And so that's why gas clouds, just left to their own, will flatten out like pancakes as they spin. Okay. There's more to it than that, but I think that's just the easiest way to kind of introduce that concept. Okay. All right, so that's how galaxies form. Good stuff. That's why spiral galaxies are spirals. But as I think Gianni pointed out last week, irregular galaxies, elliptical galaxies formed by other galaxies crashing into each other, and just that creates all kind of chaos.
Yeah, with that simulation, it also makes sense why planets rotate after they're formed.
Exactly, yeah.
So if the Milky Way collides with another galaxy,
Which it will.
how much will we be affected at such a small point?
It will be gone by then, but if we were still around, not much at all. We probably wouldn't. We would notice the night sky being much more dramatic and cool looking, but we would probably be fine. Check this out. The Milky Way we now think has like 400 or so billion stars in it. The Andromeda Galaxy is probably twice the size of the Milky Way. Those two galaxies, excuse me, are going to crash together. And the chances of any two stars actually colliding in that collision are almost 0. Because, yeah, chances are none of those stars are going to collide. Oh yeah. A lot of many stars are going to be ejected into the intergalactic medium. The two central black holes will definitely merge at some point, but they're probably going to pass each other several times as they go. And the collision itself will happen over time periods of a few billion years too. It's like the galaxy collision simulations made with supercomputers are some of the coolest things, and they have a ton of YouTube videos about that stuff that I would recommend checking out. Okay.
I'll just stick around and watch it happen.
Or just stick around. It's a super slow motion, though. I mean,
I can get a snack whenever I want. I know it won't come this much.
nope. See, same angular momentum. Same angular momentum. So I also want to point this out. So this is a simulation showing, if you remember last year, Logan. Remember last year when I showed you this, and
Yeah.
this is going to show the trajectories of the two Voyager spacecraft, the farthest things away from the Earth that are man-made that will never come back. They actually carry messages from us to any potential beings that might find them. But here's the Earth. There goes Voyager 2, which strangely was launched before Voyager 1. There goes Voyager 1. And these are the paths that they will take, or that they took. But they're still going. They're like pretty much at the edge of the solar system now. Watch what happens. They're not going fast enough to get them where we wanted to go. So what we do is we send them straight at like Jupiter and Saturn, and do a something called a gravitational assist, which is a way of like slingshotting them. They're only going like 20,000 miles an hour here. But that's it. But we want them going like 35, 40,000 miles an hour. And so how can we get that to happen without fuel? Because they're out of fuel, right? It takes a lot of fuel to get things out there. So how can you pick up a lot more speed without burning a bunch more fuel? Well, you just send them by Jupiter and Saturn. I thought this happened fast. There's Jupiter. You just send them by Jupiter and watch what happens. Picked up speed greatly. Huge amount of speed. Same thing with Voyager 2. And then they go by, and I think they get one from Saturn as well. And they actually...
How much did they?
So this was all just casually calculated.
Oh, yeah, yeah.
Yeah.
Now, they didn't even plan it. They just shot... They're like, yeah, right about there, and they just shot it that way, yeah. So,
Fraction of an angle to just put it off, just barely, but they just eyeballed it.
yeah, they just eyeballed it, yeah. It's not true for those at home. Okay.
The strongest eyeball.
The strongest what?
Eyeball ever created.
Yes, yes, very, very good eyeballs. So, how do they do that? Because if Jupiter is moving in a straight line, and we want to pick up speed with our satellite, well, we could just send the satellite this way, and then it picks up speed as it goes down to Jupiter. Unfortunately, what happens?
Boom.
It crashes into Jupiter. So if you don't want it to crash into Jupiter, then you just say, all right, well, we need to redirect it somehow so it comes back out. Well, then you haven't gained any energy at that point. You haven't gained any speed, right? Because you gain energy on the way down and then you lose energy on the way up. So it's not that they're trying to like gain kinetic energy directly from Jupiter. What you want to do is use its angular momentum, because Jupiter's not moving in a straight line. If it moved in a straight line, this wouldn't work. Jupiter is curving, and so you can think of it as kind of a slingshot, right? You send the probe in, so it comes right here, and then as it's curving around the sun, it kind of slingshots it out. And so there's a lot more to it than that, and I'm not very good at describing it because I don't think I have the best understanding of it. But Jupiter's moving in an arc. It has angular momentum. It's moving it has angular momentum that's actually changing. And so what the satellites do, they come in and they steal some of the angular momentum and convert it to linear momentum. And so each time we do this, one of these gravitational assists, a little bit of Jupiter's angular momentum gets taken away, but Jupiter's so big that it's completely negligible. But it gives the satellites a huge boost in speed. Huge boost.
Imagine if we miscalculated.
Yeah, they did this in the 70s, so people are smart. People knew it. But this is before modern computers. This is when their computers that they were using to do these calculations were not as powerful as the phones that you have in your pockets now. And they did it several times. Several times they do this.
So, even though, like, at the instant or like at the time period that this happens, still works.
It still works, yeah. Even though Jupiter, yeah, for that the time period where Voyager was like in close proximity, Jupiter's kind of traveling in just a straight line, but it's still curving a little bit. And because Jupiter's so massive, that little bit of curvature is more than enough to get those satellites a huge boost in speed. And Jupiter's massive. Jupiter, you get the largest gravitational assist from. If you add up all the mass in the solar system without the sun, Jupiter's got about half of it. And that's all the planets, all the asteroids, the literally trillions of comets that are out there in the Oort cloud. I'll add up all that mass without Jupiter and the sun, and all that mass is about half of Jupiter's mass. So it's about the same as Jupiter's mass. It's giant.
That's like 99% of the solar system.
And then you get the sun that's got 99% of the mass of the solar system, yeah. So the remaining less than 1%, half of that is Jupiter. It's pretty cool stuff. Okay. So, that's the cool stuff. Now let's talk about, not the boring stuff. To some students, the boring stuff. But first I want to talk about cross products. A little more detail real quick. Right. You know, you learn all the properties, you learn the multiplicative property, you learn the commutative, the associative, you learn all the rules for differentiation and things like that. Well, there's another set of rules for vectors and vector operations. And so one thing that you'll want to learn eventually is how do you do the derivative of a cross product. I forgot to bring it in, but my Introduction to Quantum Mechanics textbook, it's like this thin. It's not even a big book. There's like no colored pictures in it or anything, and it's one of the most expensive books I ever had to buy. But the formula chart at the beginning in the front pages is just a bunch of vector operations, operations, and how to do derivatives and integrals of them. And so it's useful. I didn't know any of that stuff until I was in college, so I feel like if I had seen it before, it might have helped me a little bit. But let's say I want to do the derivative of this. If I want to do the derivative with respect to, I don't know, time, but it could be anything. I want to do the derivative with respect to time, where time is x, of the cross product of A and B. Well, just like your product rule, this is similar to the product rule. This is equal to the derivative of vector A with respect to time crossed with vector B plus vector A crossed with the derivative of vector B. And this is something that you can prove, right, just using vectors and derivatives and stuff. And so I'm actually going to prove something that we stated right at the beginning of class. Well, we know that we know that angular momentum is position crossed with the linear momentum, right? If I have a point mass that has linear momentum, then I pick a point in space, draw a position vector, cross that, that's how you say it, cross that position vector with the momentum vector, and that will be my angular momentum vector, which is mutually perpendicular to both of these vectors. Well, if I want to do the derivative of the cross product of the angular momentum with respect to time, I use this property of the cross product to say, well, that's the derivative of position with respect to time crossed with the momentum, linear momentum, plus the position crossed with the derivative of momentum with respect to time. What's that?
What is the derivative of force?
Force.
Yeah.
Not the derivative. Oh, so it's the derivative of angular momentum force?
Yes.
Stop ruining it. I need to know. Spoilers.
Yes, you are correct. No one listened to the gentleman in the back. So the derivative of the angular momentum with respect to time. What's dRdt though? I mean, here, yeah, but we haven't dealt with this. What's dRdt? Velocity. So the velocity crossed with the linear momentum plus r, or position crossed with as you pointed out, the force. Change in momentum with respect to time is average force. Instantaneous change in momentum with respect to time is instantaneous force, or just the force at that moment. All right. Well, what's linear velocity crossed with linear momentum? The magnitude of it is linear velocity times linear momentum times the sine of the angle between them. What's the angle between an object's velocity and momentum?
It should be 180 or 0.
Zero.
Oh.
Well, they have to be. It's zero.
Yeah.
It's never 180 degrees. It's always zero.
0.
If I'm moving this way, my momentum's that way. If I'm moving this way, my momentum's that way. Right? So V cross P is zero. Anytime, and it would work if it was anti-parallel, right? If they were in opposite directions. Anytime two vectors are in the same direction or in opposite directions, then their cross product is always zero. And you see that a lot when you do use these vector properties to define physics quantities. So this is just zero, which tells me that the derivative of the angular momentum with respect to time is the cross product R of R and F. And the cross product of R and F is torque. I like the excitement. So here's a definition of torque, and we should expect this because the derivative of linear momentum with respect to time is force. So the derivative of angular momentum with respect to time should be torque. But here's the proof. Right?
Who could have seen that coming?
Yeah, who could have seen that? So it makes sense?
Yeah.
So that's why, but at the beginning, remember, it's external torques. External torques can cause changes in angular momentum. But in the system that I showed you where you had a bunch of different particles colliding, there was no external torque there. Yeah, there was torques, there was forces and positions and a lot of really complicated stuff. But that's what's kind of nice about angular momentum, right? It can take a lot of complicated stuff and boil it down to a single quantity, right? Which is pretty convenient. Anyway, make sense? All right. So a couple other things I want to go over. We will continue working on the quest assignment with the time left today, and we will also work on it in class tomorrow, and it will be due tomorrow night. Okay. And remember, it is a major goal. So the last problems on the quest assignment will kind of deal with what we're going to talk about now. So one of the most common types of angular momentum problems is where you have two disks that are aligned, or they have the same rotation axis passing through their centers. And we would say, here I am going to indicate, let's say this guy is a, I'll call that omega 1. And we'll say this guy's spinning the opposite direction. So he's like, omega 2. And then they come and they stick together like an inelastic collision, and then they will rotate again as one object. Right? You see what I'm saying there? So, just like with the linear momentum problem where you have two masses stick together and you deal with them like an inelastic collision, we just say the initial angular momentum equals the final angular momentum. Well, I have two angular momenta at the beginning. So I just say the rotational inertia 1 times the angular velocity 1 plus the rotational inertia 2 times the angular velocity 2, which is this guy, is going to equal, well, after they collide and stick together, forgot to draw that one, it'll look like this. They collide and they stick together, and they will then, so this has rotational inertia I1 plus I2, and there will be some final angular velocity, and you'll have to be careful with your signs so that you know what direction they'll actually be rotating afterwards, and I'll call that omega f, some final velocity, angular velocity after the collision. And so this would just be I1 plus I2 times final angular velocity. very often this kind of problem asks you what that final angular velocity is. And if these are disks, this is just 1/2 mr squared, 1/2 mr m2r squared, and all that good stuff, right? So I'm not gonna, it's not that difficult if you understand conservation of angular momentum. Mr. Graham? Hey. Sure. Okay. Bradley?
Yeah.
You gotta see Mr. Waldman?
Who's that?
AP office.
It's the new
It's the ball head dude, Mr.
The what?
Mr. Shiny.
He said bring your stuff.
Oh, somebody's
Oh,
getting
my
quarantined.
Oh, I hope not.
That would,
I don't think you're coming back.
that would really suck.
Bye, Bradley.
I would probably cry.
Don't cry.
Bye.
Remember my Zoom meetings.
Have a good rest of the semester.
Okay, so we good with that?
I don't feel good.
Okay, so another one, and I just realized lately that Khan Academy has gotten significantly better than the last time I saw Khan Academy. It was years and years ago. So I actually found a pretty good video that describes, it kind of reiterates some points.
So is it Pro Academy now?
You're fired.
Do you see you're
Huh?
Do you say you're hired or fired?
Fired. You're all fired.
Okay.
No, no.
Yay.
Then we can go home.
No.
We can just follow Bradley.
We have to do the question for fired.
Okay, so this is another very common type of problem. Realize that, and he's going to walk through it, and he's going to point out some things. I just want to make sure that you, it's not even Khan, it's someone he employs now. I want to make sure that you just pay attention to the things like angular momentum of an object in a straight line. You got to wrap your brains around that. The angular momentum of the object, you can determine it at any time, but there's a convenient time to determine, or a convenient set of values to determine the angular momentum of a point mass with respect to a point, and that's waiting until the angle between the position vector and the linear momentum is 90 degrees, because then the sine of 90 is just 1, and it makes things easier. So anyway, I'm just going to play this video. I'm going to remember to turn the microphone around so hopefully they can hear at home. Although I think I did link it on the Canvas page. All right. So Khan Academy has gotten better. He was like the first one on the scene, you know, making YouTube videos for this kind of stuff years and years ago. But other people, I feel like, kind of took the ball and ran with it. But I think he's built something that's pretty good now. There's a very common example problem. You can replace the rod with a disc or with any object that you have the rotational inertia of. You can change the pivot axis from the end to the middle, same thing.
What's up, everybody? I want to show you something kind of crazy. When I first heard about this, it really bothered me, so if you have to have a reaction, it's natural, but I'll help you get over it, and it'll hopefully make sense by the end of this. The crazy thing is this: if you got an object, say this ball, say this is a bouncy ball, and it's going in a straight line, it can have angular momentum. And I'll say that again. A ball traveling in a straight line can have angular momentum. When I first heard this, I was like, what? There's no way this ball can have angular momentum. It's moving in a straight line. It's not even rotating. Don't things have to have some sort of rotational motion in order to have angular momentum? And it turns out they don't. But the proper response, it gets a little weird. Before I show you how it makes sense, let me show you this. It doesn't even have to have angular momentum. It could be that this has no angular momentum. And before you get really confused, let me explain. The proper response to someone saying, does this ball have angular momentum, is to respond with angular momentum about which axis. So you have to specify the axis. So the axis is the point about which you're going to consider the rotation. So if I said, does this ball have angular momentum? If the ball is moving in a straight line, does it have angular momentum relative to this axis? That's a proper question. But if I just ask you, does this ball have angular momentum, and don't specify the axis, then it's not even a meaningful question. So let's try to figure this out. Why does this ball have angular momentum at all, regardless of any axis, right? That's the confusing part. It's not even rotating. How does a ball moving in a straight line have angular momentum? We know it has regular momentum because obviously mass and velocity have momentum, but it's not even rotating. How can it have angular momentum? First, let me explain conceptually why that makes sense. So imagine you have this bar here, right? This bar, say this is a bird's eye view. We're looking down. This bar is attached to an axis that can rotate, and we're looking down. This is on a tabletop. Let's say this is all happening on a tabletop, and we're looking down at it. Imagine we throw this ball, right? This ball, moving in a straight line, hits the edge of this bar, and this bar, what is it going to do? You know what it's going to do. It's going to rotate. It's going to rotate about its axis. And now the question is, this bar initially had no angular momentum, because the bar was just sitting here at rest. Then it did have angular momentum after the ball hit it, right? Because objects rotating around in a circle have angular momentum. Where did this bar get its angular momentum? Well, the only thing that bar interacted with was this ball. So this ball must have come in and transferred some angular momentum to the bar, because where else would the bar get the angular momentum from? I mean, if we believe in conservation of angular momentum, that angular momentum has to come from somewhere. It can't just pop out of nowhere. So the only place that angular momentum that the bar got had to be from the ball, because that was the only other thing in the problem. So this ball had to come in with its own angular momentum, even though it was traveling in a straight line, which is kind of weird, but that's the case. That's physics. And that's also why it makes sense why it depends on where the axis is. Because if I take this bar and move this bar over to here instead, right? So now we consider our axis over at this point. Well, imagine the ball hitting the bar at the axis point, right? It just hits right there, boink. It's not even going to cause that bar to rotate because it's hitting it at the axis. So the location of the axis is going to determine how much angular momentum an object has that's moving in a straight line, because if it hits this bar at the axis, it's going to transfer no angular momentum. But if it hits this bar far away from the axis, it can transfer a lot of angular momentum, because the bar is going to rotate a lot, because there was a large amount of torque applied, since this force was applied at a distance that was far away from the axis. Now you
Realize that that's an internal torque, though. It's not an external torque. That's why the angular momentum is still conserved.
still might not be all that impressed. It might be like, that just sounded like a bunch of physics witchcraft to me. How do you calculate this exactly? How do you exactly define what we mean by the fact that this ball has angular momentum? So let's define this exactly. Let's say this ball has a speed or a velocity v, and the mass of the ball, we'll say the mass of this ball is m, and the distance from the axis to the ball, let's just draw that on here, so that's going to be from the axis to the ball, we'll call that little r. And now we can define precisely what we mean by the angular momentum of a point mass. The angular momentum of a point mass, L is the symbol for angular momentum, is going to be m, the mass of the ball, so the mass of the object that has the angular momentum, times v, the speed of the ball. And this is looking pretty familiar because m times v is just momentum. So this is regular momentum, but if you just left it like this, that'd just be regular momentum. You have to turn this into angular momentum, and you do that by multiplying by r. And r is defined to be the distance from the axis, or your origin, to the mass that you're considering. And so this is the total distance r. But you're not done yet. You need one more term in here. That's going to be sine of the angle. Sine of the angle between the velocity and the r vector. So you're going to have sine of this angle right here, the angle between the velocity and the r vector. Now I'm being a little sloppy, so people paying attention out there that already know this might be a little concerned. Technically r goes from the axis to the mass, so this isn't the angle between v and r. Technically, you have to imagine r being extended out this way, and then that's the angle, but because we're taking sine of either of these angles are supplementary. The sine of either of them are giving you the same number, so you're safe by just taking any angle here between v and r, and you'll get the right answer. But this is complicated. If I were you, I'd be like, oh man, mdr sine theta, I don't want to have to figure out what the angles are between things. And if you don't, there's a trick. So check this out. If you just consider, what does r sine theta even mean? What is this, right? Visually, what does this represent on here? Well, here's the total amount r, here's theta. Think about it, r times sine theta. Imagine making a triangle out of this. Make a triangle that goes from there to there, from here to here. So you've got this triangle here. R times sine theta is just this right here. So it's just this length right here, this opposite side. Because, if you didn't catch that, that might be a little bit weird. So sine of theta is always opposite over hypotenuse. And
You guys know
on
that, right?
opposite side, opposite to that angle is just r. So that's just r. And then the hypotenuse, is just this little r, is big r. We call that little r. So if I multiply both sides by little r, I'll get that r times sine theta, and this theta here is this theta here, so this is that theta right there. R sine theta is just equal to this right here. And what is this? This is just this point of closest approach. So when the ball makes it to this point right here, when the ball gets to this point, going this way at some speed v, it's going to be r away. So all you really need to do to find the angular momentum of an object, of a point mass, even if that point mass is going in a straight line, is take the mass times v, and then if you don't want to have to worry about sine theta and all of that mess, just multiply by r, which is the distance of closest approach to the axis. So that's what this r is. This r is the distance of closest approach to the axis. And that's just this right here. That's just this distance right here between the axis and the point where the ball will be closest to the axis. So that's this distance right here. Turns out this r sine theta is always just equal to that. So you can make life easy. Just imagine when this ball comes in, at what point is it closest to the axis? That would be this point. And then how far is it when it is closest? That gives you this r value. You can take mvr. That gives you the angular momentum of this point mass. Tells you the total amount of angular momentum that thing could transfer to something else if it lost all of its angular momentum. That's how much angular momentum something like that rod could get. So let's try an example. Let's do this example. It's actually a classic. A ball hitting a rod. Man, I'm telling you, physics teachers and professors, they love this thing. You should know how to do this. Let's get you prepared here. So let's say this ball comes in. It hits a rod, right? So the ball's going to come in. Ball's going to hit a rod. And let's put some numbers on this thing so we can actually solve this example. Let's say the ball had a mass of 5 kilograms. It was going 8 meters per second. Hits the end of the rod, and the rod is 10 kilograms, 4 meters long. Let's assume this rod has uniform density. So this rod has a nice mass distributed evenly throughout it, and it can rotate around the end. So when the ball gets in here, strikes the end of the rod's going to rotate around its axis. And let's make another assumption. Let's assume when this ball does hit the rod, the ball stops. So after hitting the rod, the ball is stopped and the rod moves on with all the angular momentum that the ball had. That would just make.
Just so you guys know, sometimes the ball sticks, in which case it has angular momentum again. You know, right? It'll still contain some angular momentum afterwards. In which case you'd expect the rod to be rotating more slowly because now the mass has some angular momentum as well. Sometimes it bounces off in the opposite direction, but the same principles here will apply. It's just the equation will be a little simpler here than it would be in those two cases.
Make it a little easier. We'll talk about what to do if that doesn't happen. It's not that much harder. Let's just say that's the case initially here. So move the ball back over here. How do we solve this problem? Well, we're going to try to use conservation of angular momentum. We're going to say that even though there's an axis here exerting a force, the force that axis is going to exert on our system is going to exert 0 torque because the R value, right, torque is equal to RF sine theta. And if the R is 0, R is the distance from the axis to the force. If R is 0, it's going to be no torque exerted by that axis. If there's no torque exerted externally, there's no change in angular momentum of the system. So this system of ball and rod is going to have no external torque on it. That means the angular momentum has to stay the same. This is a classic conservation of angular momentum problem. So we're going to say that L initial, the initial angular momentum, has to equal the final angular momentum. We just say for our entire system, what had angular momentum initially? Well, it was this mass. So this mass had the angular momentum. How do we find that? Remember, it's m times v times r, and the r is that distance of closest approach. So we're going to use this here for the whole 4 meters as this r. Yes, you can consider this hypotenuse r and the sine of an angle, but that's harder than it needs to be. You can find angular momentum, MdR. That's going to equal the final angular momentum. Remember, this ball stops. So since this ball comes to rest, and it's only the bar that has angular momentum afterward, we only have to worry about the angular momentum of the bar on the final side. And to find the angular momentum of an extended object or rigid object, you can use I omega. And this would let us solve for what is the final angular velocity of this rod after the collision. So that's what we want to figure out. What is the final angular velocity of the rod after the collision? Now we can figure it out. We know the mass of the ball, M. We know the speed of the ball initially. We know the R, line of closest approach, that's 4 meters. What's the moment of inertia here? Well, it's just going to be 1/3 ml squared. Let me clean this up a little bit. Let me take this. I'll just copy that, put that right down over here, and we can say that the moment of inertia of a mass of a rod, it's rotating around its end, is always going to be 1/3 ml squared. So 1/3 times the mass of the rod times the length of the rod squared, which is going to be the same as this r here, because this ball's line of closest approach was just equal to the entire length of the rod since it struck it at the very end, and then times omega. So we can solve this for omega now. We can say that omega, I'm going to bring this down around here so it has some room. Omega final of the rod is just going to be what? It's going to be mass of the ball times the initial speed of the ball times the line of closest approach. And I'm going to divide by 1/3 the mass of the rod times the length of the rod. I can just call that r. It's the same variable. Length of the rod squared. And that's what I get. So I can cancel off one of these r's, and then I can plug in numbers. If I wanted to actually get a number, I'd say that the final angular velocity of this rod is going to be 5 kilograms. That was the mass of the ball, times 8 meters per second. That was the initial speed of the ball. And then I'm going to divide by 1/3 of the mass of the rod was 10 kilograms. And then the length of the rod, which is this line of closest approach, was 4 meters. And if you solve all that, you get 3 radians per second. So that's how much angular speed or angular velocity this rod had after the ball hit it and transferred the ball's angular momentum into the rod, giving the rod angular momentum, causing it to spin around and rotate at 3 radians per second. Now, what would be different if, instead of getting stopped, the ball bounced backward, let's say at 2 meters per second? Well, now the final angular momentum wouldn't just be the angular momentum of the rod. You'd have to include the angular momentum of the ball. But here's the tricky part. If the ball was coming in this way initially, which would mean it has angular momentum essentially around this way, and the ball went backward the other way, now it has angular momentum around this way, you'd have to have a negative sign in here. In other words, when you include this angular momentum on the right-hand side, you have to treat it as, well, there's a couple ways you could do it. You could just do plus if you wanted to, and then you do the mass of the ball times this negative 2 meters per second times the same 4 meters as the line of closest approach. You could put the negative here with a plus out here, or you could put the negative out here with a plus in here. You could do it either way, but this term for the final angular momentum of the ball would have to have the opposite sign as this term for the initial angular momentum of the ball. So recapping, a ball can have angular momentum even if it's moving in a straight line, and you can determine the angular momentum of that ball by using mv r sine theta, where r is the distance from the axis to the point where the ball is, and theta is the angle between r and the velocity. Or if you don't want to use r sine theta, you can use mv capital R, where this capital R represents the closest that ball will ever be to the axis as it's traveling along a straight line.
So I honestly feel like he did a better job of explaining that than I did the other day. So yeah, Khan Academy has gotten pretty good. It's gotten pretty good, and I think it goes up to calculus-based physics as well, because this is still just algebra-based right here. Anyway, so that's all I got for today. Go away now. Just kidding.